smart ladies. So it's my pleasure to introduce Ed Nissen, who is visiting us from the Colorado School of Mines, where he's an assistant professor. I was in Golden last night, actually. It's a lovely place. He grew up in London and did his undergraduate and master's degrees in geology at Cambridge, and then moved to Oxford, where his PhD focused on active tectonics in the Alpine Himalayan earthquake belt using satellite observations with a focus on InSAR, fieldwork, and seismology. And after graduating in 2008, he did a 3-year postdoc in Cambridge. He's making good use of these schools. And then a 1-year postdoc at Arizona State University, where he started working with high-resolution topography. And he's been at the School of Mines since a year ago this month. Please join me in welcoming Ed.
Thank you very much. So actually, yeah, my first semester as a mines employee, I was actually given leave of absence to finish my postdoc in Arizona. So what I'll talk about today is the work I've been doing there with Ramon Arrowsmith, who many of you may know, and Sri Saripalli and Aravindan Krishnan. And my other collaborator on the work I'll show today is Tadashi Maruyama, who's a Japanese colleague. And then this work is sponsored jointly by NSF and SCEC. So I'll plug them. So first question, does anyone know where this scene is from? I think Chris does. So this is a famous, this is Wallace Creek in the Carrizo Plain on the central part of the San Andreas Fault. This is probably the most famous set of stream offsets anywhere in the world. And they're beautifully captured here in this Lidar topography. So Lidar is, today I'm going to talk about airborne Lidar primarily. There's also terrestrial Lidar. But it stands for light detection and ranging. And it's essentially a very high resolution laser scanning map of the Earth's surface taken by a laser scanner on board an aeroplane. And you can see these beautiful stream offsets just visually here. I think this one here is Wallace Creek itself. And the top part of the image is the North American plate, which is moving to the south, and the lower part is the Pacific plate moving north. And you can see these streams have been offset cumulatively in many, many earthquakes. And this is one of the most famous kind of most stunning results from Lidar, this revolution in high-resolution topography that's happened over the last few years. So aside to these very obvious large offsets, you can also see much smaller stream offsets across this San Andreas Fault here. And if you can, with the topography, you can measure the amounts by which these streams are offset. And one of the nice results from this particular study, which was by Olaf Zielke in Arizona, ASU, is that when you look at these, you measure these offsets all the way along this part of the San Andreas Fault, and you find that they fall into these very discrete sets of offsets. So there's one set at 5 meters, another one at 10 meters in the blue here, another one at 15 meters. So this is the amount of offset of the stream by distance along the fault. And the way these are interpreted is that the 5-meter offsets are from the last earthquake, which is a historical event from 1857. There's a few written records of this earthquake. The 10-meter offsets are the 1857 earthquake plus the previous earthquake, so 2 earthquakes. And the 15-meter offsets are the last 3. And then you can see some 20-meter and 25-meter offsets. So one of the interesting things from this study was that the behavior of this part of the San Andreas Fault seems to be quite uniform. Every earthquake is slipping about 5 meters. And that can help inform our hazard maps of the area. So the key thing about this study was the use of the new use of Lidar topography. This data set had only been available for a few years. And the key thing from an earthquake scientist point of view is that the scale of the resolution of the Lidar is sub-meter, and it's less than the amount of slip that you would expect to occur in large earthquakes. And this is the first topographic data sets that we've had spanning wide regions for which this is true. So what I'm going to talk about is not just, this is obviously a single Lidar data set, but what I'm going to talk about today is, I've cheesily called it 4D topography, So it's using Lidar, but in a multi-temporal fashion, so repeat Lidar data sets. So we started thinking about how we would go about doing this, because really in the last sort of couple of years, the number of Lidar data sets that are publicly available, certainly in the US, has really exploded. So this is just a screen grab from Open Topography, which is a website I'm sure most of you know. This is basically all of the Lidar data sets that are free to download. Any member of the public can download these all across the United States. And from an earthquake scientist point of view, obviously we're mostly interested in the western part of the US. And if I pull up a map of California, you can see that actually most of the major active faults in California are now covered by airborne Lidar. So the red lines here are faults with Lidar data sets along them, and the black ones are the few that are still to be scanned. So the idea that we had was that obviously if an earthquake occurs on one of these faults, we have an existing baseline of topography against which we could compare a post-earthquake Lidar scan. So we have one data set before the earthquake, we have the shape of the Earth's surface before the earthquake happens, we go and rescan it using the same technology, and we'd be able to compare the two topographic data sets. And the beautiful thing about Lidar compared to some other geodetic imaging techniques, most obviously InSAR, is that we should be able to actually resolve three-dimensional displacements, because it's a three-dimensional shape of the Earth's surface. If we compare it before and after the earthquake, we should be able to resolve the full three-dimensional displacement at the Earth's surface. So at this point, I'm just going to go back in time just to show you kind of how new this stuff is. So this is the same data set. This is now in map view, no perspective view. This is Wallace Creek up here. The San Andreas fault is very obvious. So just a few years ago, the best kind of global DEM available, and this is still true globally, the best DEM available is a 30-meter resolution, the GDEM derived from ASTER satellite images. And you can straight away see a lot of the detail that we see in the Lidar is lost. So in 2005, the best we could do is the Shuttle Radar Topography mission, which is a satellite radar mission, which gave us 90-meter pixels. And straight away, you can see, well, maybe there's a fault along here, but you can't see any of the stream offsets. And then before 2005, the best global data set was actually 1 kilometer resolution. It's true that in the US it was better than that, but globally, even 10 years ago, you really couldn't do much with topography. So today we can do a lot better. So I'm going to briefly introduce Lidar topography, how it's actually generated. The methods I'm going to talk about would actually work with any high-resolution topographic data set, but all the results we've got so far from airborne Lidar. So you have an aeroplane with a laser scanner on the underside, and it's basically scanning these zigzag scan lines across the landscape. Each of these red dots is an individual laser beam that's come from the aeroplane, backscattered off the Earth's surface, and is picked up back at the plane. And basically, the timing of that pulse of energy is used to estimate the distance between the aeroplane and the ground, that point on the ground. And then if you know the position of the aeroplane very accurately from GPS and various leveling instruments on board the aeroplane, you can work out the position and geographical coordinates of that point on the ground. And the accuracy, well, first of all, the footprint of one of these pulses, by the time it hits the ground, it's usually maybe about 20 centimeters wide. The aeroplane is typically flying, low flying, but maybe a couple of kilometers elevation. And the accuracy, the vertical accuracy is very good. It's about 5 centimeters. The horizontal, a little bit less, maybe 20 centimeters. And typically, the swath width, so basically the width of the data set that you would get would be a few hundred meters, and typically you have several scan lines that are basically overlapping, used to make wider swaths, maybe up to a kilometer or two in width. So what you basically get out of this is this cloud of points. We call it a point cloud, which is basically an irregularly spaced set of X, Y, and Z coordinates. And early data sets, typically there was maybe 1 point per square meter. Nowadays, it's routine to have more than 10 per square meter. And the way that you usually visualize LiDAR is as a DEM. So you basically take this irregular point cloud and you grid it into something that's basically pixel-based, so regular spaced. So one way of doing that is to basically define a node spacing and a search radius. And then you basically, for each of these points, we're going to assign an elevation value. And that might be based on the minimum or the maximum or maybe some average of all of the points lying within the search radius. So that's one way of turning a regular point cloud into a DEM. So this is now would be a digital elevation model. One of the beautiful things about airborne LiDAR is its ability to actually see through vegetation. So this is basically a perspective view of a point cloud. Chris may have actually made this image because it was grabbed from Open Topography. So what you can see is you can see some trees here and then this kind of bare hillside. One of the beautiful things about LiDAR is that it can kind of see through vegetation. So if you imagine a laser beam passing downwards through a tree or some kind of vegetation, some of the energy may actually get through the leaves, hit the ground, and bounce back up. So you actually, at the aeroplane, you actually measure discrete returns, some from the canopy, and hopefully one from the ground. And actually, as a geologist, what you usually do is you strip off the vegetation to leave the ground returns, although biologists might do the opposite. So that's a brief introduction to LiDAR, so apologies if that was very familiar to some of you. So now I'm going to talk about LiDAR in repeat mode. So obviously, measuring earthquakes, InSAR is currently the sort of primary means of detecting and measuring surface deformation of the Earth occurring in an earthquake. But InSAR obviously only measures the motion of the ground surface and the satellite line of sight. So it's actually only one component of what is a three-dimensional vector of the Earth's surface. One of the things about LiDAR, this is before earthquake LiDAR and after earthquake LiDAR, because it's a three-dimensional measurement, we should be able to actually resolve the displacements in 3 dimensions. So this is one advantage that differential LiDAR or repeat LiDAR should have over InSAR. InSAR is a satellite. Yeah. No, it's going to be a very different method for doing the differencing. So I'll come on to how we do it in a second. This is just kind of to give you, obvious pros and cons of the two methods before I get into the nitty-gritty. So InSAR is a satellite-based technique, and interferograms typically cover many tens of kilometers across and along azimuth. So InSAR is very good at measuring far-field deformation. So this is an interferogram spanning the Darfield earthquake in New Zealand. This is the surface fault here. Here's Christchurch, which was hit in a destructive aftershock. These fringes are basically, these coloured fringes are basically contours of ground displacement occurring in the earthquake. And what you can see is many tens of kilometers away from the fault, we still have InSAR signal. So it's very good at measuring far-field deformation. What you also notice is this gap, this grey patch here, where you can see the underlying grey shaded topography along the surface faulting. So one of the weaknesses of InSAR is it often breaks down where gradients in surface deformation are too high for it to actually produce coherent fringes. So InSAR is very, very good at far-field deformation, but it's less good at measuring near-field deformation along the actual surface fault. So this is where LiDAR should have an advantage. It won't decorrelate close to the fault. And actually, most LiDAR data sets are anyway focused very narrowly along fault zones. So we're going to be restricted to areas where we have pre-existing LiDAR topography. So this is just a LiDAR scene of the Darfield rupture. You can actually see these beautiful en-echelon kind of ridges, I guess, push-up ridges caused by strike slip in that earthquake. This is a single LiDAR scene, so there's no different thing done here. So the first major rupture for which we had pre- and post-earthquake LiDAR was an earthquake in Mexico, just over the border. between California and Mexico. So San Diego is down here. This is the Salton Sea and the Coachella Valley up here. So this is basically part of the San Andreas fault system. And there was a large strike slip earthquake here in 2010. And the area actually already contained a regional Lidar data set. It was very low quality as Lidar goes. It had only about 1 point every 10 by 10 meters, roughly. But after the earthquake, it was rescanned with a much higher resolution data set. And this is a science paper headed by Mike Oskin at UC Davis, where they differenced these two data sets. So they simply subtracted the elevations of the pre-earthquake data set from the post-earthquake data set. And they're looking at the difference in elevation. And this is the full length of the rupture, which is, I think is about 60 kilometers long, something like that. So anyway, zooming in on some of these areas. So this is the pre-earthquake LiDAR data set. This is the post-earthquake LiDAR data set. And you can see these scarps forming up in the desert here. These are clearly signs of surface faulting. And if we difference the two data sets, we can subtract them. These blue areas have gone down in the earthquake, and the red areas have gone up. So you can see some beautiful details of faulting in the desert there. Moving along, this is just another example. So this is the pre-earthquake data set and the post-earthquake data set. You can see this light line along here. That's actually a northeast-facing scarp. It's illuminated by the topography. And you can see, if I subtract one from the other, you can see this side of the fault has gone up and this side has gone down a little bit. So slightly darker colors here, slightly lighter colors here, warmer colors. But an issue with this method is obviously it's great if you have vertical deformation, but this is primarily a strike slip earthquake. So in some areas where it's pure strike slip, you can difference the pre-earthquake and the post-earthquake data set, and you don't really see much. So actually there's a scarp running through here. You might be able to make it out along this line here. That's the surface rupture, but the difference map doesn't look particularly interesting. So the simple DEM differencing can reveal some nice sort of complex surface rupturing patterns, but the elevation changes don't actually directly equate to surface displacements because we always have lateral component of deformation to worry about. So we're going to try, we need to a method that can basically match the two images in 3 dimensions. So the method we use is called the iterative closest point algorithm, ICP. It was invented in the early 1990s primarily as a way of registering medical images. So if you go into a hospital to have an operation, they'll typically scan your body before the operation, and then they'll scan it afterwards to compare the two images. One important thing in this in medical imaging is to actually be able to accurately match the two images, so you can actually compare point to point the features in your body. So this is ICP was basically developed to do this. It's a method for registering or aligning two sets of points in 3 dimensions. So we're going to use it to register to landscape scenes, so pre-earthquake or other event and post-earthquake. And just like with the CAT scan, we can do this to irregular point clouds. These don't have to be gridded DEMs, although it works for gridded DEMs too. You can do it to any kind of cloud-based point of cloud. So what we do is we basically divide our area up into these windows or cells, and we basically apply this ICP method to each window individually, and that will give us the displacement that aligns the pre-earthquake topography to the post-earthquake topography within that square, within that window. So we basically run ICP separately on each window. And when I say each window, we're talking about a pair of data sets, a pre-earthquake window and a post-earthquake window. So for each window, this is what we do. This is a cross-section through one of these windows. This is just a little bit of topography. Here's our plane measuring that topography before the earthquake. We have a point cloud. Then the earthquake happens, and we come back afterwards, and we'll remeasure it. And LiDAR technology is always improving, so typically the post-event point cloud will be higher resolution than the pre-event point cloud. So the iterative closest point algorithm is basically as simple as it sounds. So you basically find the closest point to each point in the pre-event point cloud. And then you find the transformation that minimizes those distances. So I'm going to basically drag the topography towards, well, drag these red points so that they're as close as possible to their closest blue point. And we do that with a rigid body transformation. So it's a translation, Tx, Ty, Tz, plus a rotation, alpha, beta, and gamma rotations around the X, Y, and Z axes. And then, so that's the closest point part. And then the iterative part is that we iterate. So you can see this first match is not particularly good. We haven't dragged the topography into its correct position. But if we repeat, what you find, if you find new closest points and repeat, and then repeat again and again and again, is that the topography is actually dragged into position. So now the pre-earthquake point cloud is now overlying the post-earthquake point cloud. And this purple line that has appeared as I've done this is basically the cumulative displacement of our pre-event topography. And if you basically add up all of these vectors, you will produce the earthquake displacement. And it will be both a displacement, a translation, and a rotation as well. So this is another neat thing about this technique compared to InSAR. We can actually measure rotations directly. So to test this method, we used it on a data set collected in Southern California, the B4 Lidar survey. And we actually made synthetic earthquakes. And we try and, first, before we come to real examples, we're going to just try it out on these synthetic earthquakes just to see how well it can reproduce the known displacements that we put into the data set. So we focused on this area, Painted Canyon, near, in the Coachella Valley. It's got a nice mix of topography, very rugged topography out here, and then flatline topography down in the Coachella Valley. So this, the data set we have is the B4 Lidar survey, which was actually collected on 5 overlapping flight lines. So what we can do with this is we can actually split those 5 flight lines such that we have independently acquired pre-earthquake and post-earthquake data. So we used the middle two, well, we used, let's call the flights 1, 2, 3, 4, and 5. And they double overlap. So we used flights 2 and 4 to form a pre-event point cloud. And we took 3, 5, and 6. I don't know why they're not numbered 1 to 5. For some reason, they were 2 to 6. Anyway, we took the outer ones and the central one to form the post-event point cloud. And then we deformed that post-event point cloud. So we added a synthetic fault to simulate the San Andreas fault. And then we moved points on the southwest side of the fault 2 meters to the northwest. Points on the northeast side went the other way by 2 meters. And we also raised them to see if we can reproduce vertical displacement. And we basically ran this ICP method at a variety of different window sizes. So these are the results for 100-meter windows. So each of these arrows is basically the displacement for a 100 by 100-meter patch of points. These are the actual input displacements. So this is how we move the data set synthetically. And these are the displacements we get out. And we can plot them in histogram form. So basically, we move the points 1.41, so the square root is 2 meters to the east and to the south and to the west and north. So we should be getting out 1.41 meters for the east displacement and the north displacement. And you can see that we're doing pretty well. The errors are about 10 centimeters, 15 centimeters. So we're doing a good job. And vertical displacement is actually very good. So the colors on here are basically the vertical displacements we get out. And you can see they're almost all about 1 meter on the northeast side and 0 meters on the southwest side. So we're doing very well. What we can then do is we can try a smaller window size. Obviously, we want as high resolution displacements as we can get. So we make the windows 50 meters, and we see if we can do as well. And you can see actually these histograms kind of degrading a little bit. So the errors are a little bit higher, 20 centimeters now for horizontal displacements. Still very good for vertical. And then we can try 25 meters and 15 meters. And you can see basically somewhere between 25 meters and 15 meters, the method kind of stops working very well. So you can see these histograms just collapsing. So the input displacements are no longer well resolved. So the method obviously works better with larger window sizes, but you can certainly get down to 50 meters, and you might be able to get down to 25 meters in terms of the resolution of your displacements. So this is the paper we wrote in GRL 2012, basically outlining this method. So our conclusions are it resolves 3D displacements very well. You can get resolutions of about 25 meters. One of the nice results is that we can also reproduce the rotation. So these are rotations in radians about a vertical axis, and you can see at the end of this is actually an earthquake where we stopped the rupture in the middle of the scene. And you can see rotations around the around the end of the rupture, which is what you expect. So it can image rotations directly. And the other nice thing is there's no need to grid or smooth the LiDAR point clouds. These are just using the raw XYZ coordinates, just the ASCII XYZ file. So most geodetic imaging techniques require pixels. They require a regular grid of points, and our method doesn't require that. So that's another strength. And it works very well even with mismatches in point cloud density. So you can actually reduce the density of the pre-earthquake data set by a factor of 10, and it gives you just as good results. So that's the boring bit out of the way. Now some case studies. So we're now going to move from America to Japan. Japan has some plus points and minus points. It's got a lot more LiDAR data than the US. It also has more earthquakes, so there's more to look at. The downside is that you have to buy the LiDAR data. It's not freely available as much of the data in the US is. So we've been quite limited in the scope of the areas that we've been able to look at. But at the same time, we have access to real data from pre and post earthquake at very high quality. So I'm going to talk about two earthquakes. Now, the tectonics of Japan, essentially you have subduction of the Pacific seafloor underneath northern Honshu. This is the Tohoku earthquake from 2011, the one that produced the big tsunami and shut down a nuclear reactor. And basically the tectonics of northern Japan are basically strongly influenced, obviously, by the subduction zone. So you can think of the tectonics in two phases. There's basically the phase where strain on the subduction interface, this is the fault between Honshu and the Pacific ocean floor, is locked. And during this phase, GPS velocities on Honshu itself show that Honshu is contracting, so it's basically shortening. And then during the earthquake, basically this upper plate rebounds, and it goes back to its original position, or something like it. And in this phase, so during the actual earthquake, you see that Honshu stretches. So you can see these velocities on the east coast are moving to the east, on the west coast they're stationary. So northern Japan anyway, goes through this two stages of kind of deformation. Between the earthquake it's contracting, during the earthquake, and immediately afterwards it's extending. And our two case studies quite nicely. One is during this stage here, it's a thrust faulting earthquake that occurred up here. And the other is a normal faulting earthquake, which was triggered by the Tohoku subduction event immediately to the south, close to Tokyo. So the interesting thing about this one was it actually occurred on a thrust fault, a fault that was mapped as a thrust fault. And it actually turned out it was a normal fault. So geologists get things wrong. So I'm going to start with the northern examples. This is a thrust earthquake, and this one actually we've only been able to get a tiny, really small patch of pre and post LiDAR data. But there are some beautiful images, and we've been able to apply our technique quite successfully. So this is a map. This is an interferogram of the earthquake. Basically, it's a west-dipping thrust fault, very shallow angle. And you can see in the interferograms, these are from two different papers, this big patch of incoherence basically along the surface faulting. So this is an area, this white area here, and this kind of mangled area, and here there are places that InSAR can't image at all. So, but what we have in this tiny little box is pre- and post-event LiDAR. So this is the pre-earthquake LiDAR dataset. This is grayscale shaded topography. This is a 2-meter DEM. And this is a post-earthquake DEM, which is 1 meter resolution. Now you can see, if I toggle between the pre-earthquake and the post-earthquake data, you can see a few things going on. So first of all, let's just subtract the two elevations. So subtracting the pre-event from the post-event elevation gives us a height change of each point on the ground. blue areas have gone down, red areas have gone up. So you can see what's happened is there's been a big landslide here. This hillside here has collapsed. So it's collapsed here, and there's a big pile of sediment at the bottom of this river valley. And that sediment has actually blocked this stream. So this stream is flowing from west to east, and it gets blocked by the landslide. So you can see the stream filling up like a bathtub. So you can see the detail of the riverbed along here in the pre-event image, and then it's all clogged up with sediment. So this is what we've got so far, just visually looking at these two images. There's another landslide off here. Another thing we can see is along a line along here, you can see a little fault scarp forming. So that's the actual earthquake rupture. And you can see there's a little bit of left lateral slip. And also the north side has gone up, and the south side has gone down. And if you visually, if you concentrate on this area here, as I toggle between the images, you'll see it moves a little bit to the east and a little bit north. If you concentrate on the area up here, you'll see it goes a little bit east and south. So visually, you can say, you can see quite a lot. This is kind of how I'd explain it visually. This is what's going on. And then this is the results. Next slide is the results of our ICP displacements. So the colored circles are the vertical displacements, and the arrows are the horizontal ones. And you can basically see what's going on here in this image. You can see these windows up here. These are 50-meter windows, I think, moving to the southeast. These ones are moving to the northwest. They're actually rotating. These ones on the east side of the fort are relatively stationary, but they're slight blue colors, so they've gone down a little bit. And ICP won't work in areas where the shape of the Earth's topography is altered completely. So it's not working in this river valley and in the landslide. So it's great for looking at earthquake surface displacements where there hasn't been mass movement. It won't work in the middle of a landslide unless it's a coherent landslide. So this just demonstrates, this was the first results we had in the real world that showed that this this method works quite nicely for earthquakes. And the displacement magnitudes also agree with field measurements made along this scarp here. So that was good. So now we're going to talk about the normal faulting earthquake. So this is our big Tohoku earthquake, the subduction thrust fault. And we're going to be looking at an area down here near the coastline. These were two faults that were mapped as thrust faults. They turn out to be normal faults. And this was our main aftershock magnitude, 6.7 aftershock normal faulting, and some smaller aftershocks which aren't really important for the story. So this is what the surface rupture looked like. It actually simultaneously ruptured two faults. This is the Idasawa fault here and the UNAVCO fault in the northeast. And the Idasawa fault had a larger amount of slip, up to 2 meters. The UNAVCO was up to about 1 meter. This is an interferogram. This is a model of the interferogram showing slip on these two faults, the Itazawa and the UNAVCO fault. And you can see that at the surface of the Itazawa fault, there's about 2 meters of slip, according to this model. But this model is based on interferograms which we know have often incoherent close to surface faulting. So the surface rupture actually comes right through this white patch here. This would be the Itazawa fault. This white line here is along the UNAVCO fault. So actually close to the earthquake rupture itself, we don't have InSAR data. So this model is actually at the surface. It's probably very accurate at depth, but at the surface it may be a little way out. But what we do have here, again, we have pre- and post-earthquake data. So we have a 2-meter bare earth DEM obtained before the earthquake, and another DEM obtained by a separate company after the earthquake. And it was actually after both earthquakes. It was after the Tohoku earthquake and the aftershock. So within this blue line, we have repeat Lidar coverage, and we can use our ICP technique. So this is the pre-event and the post-event data. If I zoom in on the post, I zoom in on part of the surface fault. You can see pre and post. You can see this scarp forming. That's the earthquake rupture coming down there. You can also see the whole image shifts to the right. I don't know if you can see that. So obviously, in an earthquake, the two sides of faults should be moving in opposite directions. But we have to remember these two scenes also span the huge subduction earthquake, the Tohoku earthquake. So actually the whole of eastern Honshu has shifted a couple of meters to the east. So actually there's a uniform shift to the east, as well as the more subtle shifts from this earthquake that we have to think about. So this is an elevation difference map. This is just subtracting the two elevations. So you can see that warmer colors here, this has gone up, colder colors here. You can also see that these blues, the lighter and darker blues and lighter and darker reds and yellows, are also lining up with the topography. So you can see this valley here, this blue here. So horizontal shifts are actually affecting the elevation difference. But if we use ICP, we get a much more coherent map. So these are 50-meter wide pixels showing basically the vertical displacements only. I'm not showing the horizontal ones for this earthquake. And you can straight away see this beautiful fault through here. Remember, I told you that ICP and this Lidar differencing technique we've developed also images rotations. So this is actually this is a map of rotations around the y-axis, so the axis going north-south. And you can see these negative rotations lining up along this line here. And essentially that is a fault scarp. So it's actually it's trying to match the topography from before the earthquake to after the earthquake when the fault's done this. And it's basically doing that by rotating that pixel around a north-south axis. So this is actually quite a nice way of, you could use this, I guess, as an automated way of picking out surface faulting. So this is Tadashi, our colleague in Japan, measuring in the field. This is how we traditionally measure slip distributions along earthquakes, either by hand or with surveying equipment. So blue dots are hand measurements, red dots are measurements made with terrestrial lidar, I think. And this is basically, this map is from north to south along that surface rupture. And you can see the amount of vertical displacement across the fault is going up and down and up and down and up again. So what we can do is we can basically actually measure the vertical displacements across our differential LiDAR map and compare those to the field measurements. So this is basically a swath of vertical displacements across this line here. So this is 0, 1 meter, 2 meters, 3 meters negative, and 1 meter positive vertical displacement. And this is distance from the rupture in hundreds of meters, or in meters, I should say. So you can see that at depth there's around 2 meters of slip, so you can draw straight lines through these two profiles. I think there's some landsliding going on up here, so these high displacements here are actually faulty, that you can ignore them. There's about 2 meters slip at depth. But actually this corresponds to this area of field measurements where the slip is less than a meter. It's only about 0.7 meters. So it's clear here that the slip is not all coming to the surface. It's actually something stopping it from coming to the surface, and that maybe it's distributed slip occurring in the upper part of the crust. And basically from this, the width of this blue box, you can estimate the depth at which that slip is becoming distributed. And it's probably a couple of 100 meters at this point. And we can continue along the fault, so moving to the south. This area here, you can see, again, it's got about 2 meters of displacement in the LiDAR profiles, but actually this corresponds to an area where there's 2 meters of measured slip at the surface by our geologist friends. So here, in contrast to this profile, in this profile, it looks like all of the slip at depth is actually making it to the surface. We move further south still. Here's another profile. Well, this was an area where there was less than half a meter of slip measured at the surface, but we still have this 2 meter displacement in the LiDAR profiles. And again, this slip deficit in the surface is probably accommodated within the top 100 meters or so of the Earth's crust. And further south still, this is an intermediate measurement. Something like 1 meter vertical displacement measured in the field, but we still have 2 meters in the LiDAR. And then south still, we have more consistent measurements here, about 1 meter, 1.75 meters in the field, and similar amount from the LiDAR profiles. So if we line up these different profiles, one of the things that we can see is that the amount of slip at depth which is given by the displacement of this horizontal line through here and a horizontal line through here, is consistent all the way down this fault zone, even though the amount of slip measured at the surface is going up and down and up and down and up again. So this is kind of confirmation of what's going on in the subsurface. It's clear that the slip is sometimes getting to the surface, but often it's not. So it's buried a little bit at depth, maybe to 100 or 200 meters. And this is an area where InSAR is unable to image. So InSAR can't give us this. The InSAR slip models, if you remember, tell us that there's 2 meters of slip at the surface. Clearly that's inconsistent with the surface measurement. So I'm going to stop there, except for a couple of sort of future outlook slides. So what I've been talking about is so far is Lidar topography and how we can use Lidar to image fault zone deformation at very high resolution and precision. I think going forward in the future, Lidar is very expensive to fly, but there are going to be some new data sets that will become available that should enable us to use these same methods to look elsewhere in areas where Lidar may not be available. So one is a satellite that's just been launched in France. It's called Pleiades. It's a successor to the SPOT satellites, and it's very high resolution, 0.7 meter pixel size at the Earth's surface. But the key thing is it's in tri-stereo. So this satellite will actually take 3 photographs of every scene on the Earth's surface that it wants to capture, or it's programmed to capture, basically a few seconds apart as it's looking off nadir, then nadir, and then back nadir. And from those, it should be able to measure roughly 2 meter resolution topography anywhere in the world. It's not going to be freely available, but SPOT data used to be available quite cheaply, and I think there's a scheme in place to offer this at a reasonable cost. And I don't know the orbital specs. I don't think it won't be a global data set. It will be targeted, so you will have to propose an area of study. So it's not quite like InSAR, for instance, or the other global, smaller than the scale of slip in very large earthquakes. So we'll be able to see big earthquakes with it. Maybe moderate earthquakes might be harder. And then last slide, just going the other way, so much less expensive but much more easily portable. Something that I've been working on in School of Mines is measuring very high resolution topography with a technique called structure for motion, which is very similar to photogrammetry, except it's even easier. We essentially suspend a camera from the underside of a UAV. Here we have a remote control helicopter or balloon, and we basically drag our balloon, or we fly our helicopter over fault zones, taking time-lapse photographs of the ground surface. And using overlapping between stereo images, we can reconstruct the landscape at about 10 centimeter resolution. So this is actually a little scarp on the San Andreas Fault in this alluvial fan here. You can just about see it in the Lidar. The Lidar is about 1 meter resolution. Our DEM is about 10 centimeter resolution. One thing it can't do is see through vegetation. So it's great in Southern California and Mongolia, but it won't work in Oregon or Washington. It's about, it could fit on this table comfortably, maybe a meter. And that's actually my last slide. So I don't really have a conclusion slide, but I would like to just point out that these new technologies and satellites are going to really, I think, make topographic differencing a real complement to InSAR and GPS in the future. And I'll leave it there. Thank you.
When you're flipping back and forth between the DEMs, you see quite a bit by your eye, almost more like optical. Do you ever take the DEMs and then do optical differencing of some sort?
You could do that. There's a group in Caltech, Sebastian Laprance, who they were the pioneers of optical pixel matching techniques, and they can apply their techniques to LiDAR data just as they can to optical imagery. So they are able to obtain 3D displacements by basically kind of moving back the horizontal offset and then subtracting the 2 DEMs, but it's not a fully 3D displacement. It's kind of 2.5D, if you like. The other advantage of our method over the pixel matching techniques is that they're matching pixels, and we're actually able to match the raw point clouds. So there's no artifacts from gridding or smoothing the data. It's basically as raw as it can be.
So when you were talking about the difference between the surface measurements of offset versus the Lidar determined offsets, does that have implications for the history of discrepancies between geodetic deformation rates versus paleoseismology?
Yeah, that's. I should have probably said that the big reason for. I mean, I guess the important result here is that a geologist who might dig a trench across a fault and measure a slip rate or a paleoseismic history, in this particular fault, if they don't choose their site, they're not lucky with the choice of their site, they're going to be seeing maybe quite a small percentage of the actual co-seismic earthquake deformation that will have happened there. So, geodesy will be giving you, if you did, say, a slip rate study somewhere where, only a small percentage of the slip actually makes it to the surface, you get a very different result than you would from GPS or InSAR. So, I mean, this is something that's been known about for a long time, discrepancies between geological rates of deformation and rates from GPS. The question is, are those discrepancies real? Are they telling us about what's going on in the Earth, changing rates of tectonics? Or is it just a measurement error, possibly in either data set? So, I guess the take-home message from that second Japanese example is that with the Lidar, we can really basically see exactly where this slip is failing to get to the surface. It's in a very shallow subsurface. So even at 200 meters depth, the slip distribution on that fault is actually quite uniform. It's about 2 meters of vertical displacement all the way down that rupture. But at the surface, it's going up from 20 centimeters to 2 meters over a very short space.
Not necessarily an error in either technique, but that there's a lot of off-fault, that the deformation is being accommodated in ways other than just kind of the piercing point model.
Yeah, it's not an error. It's just there's a gap in what we can observe between InSAR that resolves what's going on at depth and a geologist measuring offset to the surface. We've never really had pixel matching is another way of doing horizontal measurements, but certainly been no way of getting three-dimensional deformation field this close to a fault, other than by having a geologist actually go and make dodgy measurements in the field, or good measurements.